Okay. Good afternoon to everyone. I think we hope you are safe and doing good. So I'm using a mask, so sometimes my voice may not be very accurate. However, uh, it is uh, uh, unavoidable. So I'm using a mask and speaking. Okay. So uh, let me go into the here the screen. So I just in the B2 batch probably I would have told you the intricate details and the importance of the experiment what we are supposed to do today, that is a magic tea, and some of the things because of others also is there, so probably I will just review that some of the points which will be of course uh, what I mean to say always, the analysis of the result is more important than doing a experiment. And also, of course, we need to see that uh, conduction, but more than that, what is the results and basically, what we have to focus on about the results. So, with that note, probably we can just we'll go with that. So here I have that ANSYS electronic desktop. This is a simpler. I think you can see here, and the steps are given in this user guide. You can get it for the current version. This is for actually the version 9, and what we use it. Typically, the version is close to. No, let me just. There are two windows. Probably close one of the window. Okay. So this is the version we are using, typically 18 that the versions we are using, and there will be a small mismatch in the steps, but the idea of doing that and the results you will get pretty much same in the both version. Okay, so usually these complaints will come, the steps which is there in the manual which is not matching with the tool, but this is only the cosmetic change, nothing more functionally. There is no much change in the procedure. Okay, and I hope you are able to see the screen, and hope you are able to listen that. And here, what I'm going to do is first let us start with the steps, and I'll go in between the results and come back. So you tell me that what I should focus, what you just want to focus. Either I'll go to the initially on the steps, or I more talk about these results. Okay, I think it is loading. Give me a second. So this is the results, final results we get it from the Magic T. This is a 3D animation of Magic T, and also this is my accelerometer plot. This is what we expect from this experiment. I think you can see that we have designed for 4 gigahertz, and we made a frequency sweep between 3.4 to 4. So typically that the frequency is around the design frequency. I sweep the frequency and try to see that what are these S parameters. Okay, so in general, what is the magic T is? It is actually the hybrid T junction. If we have the two T is connected together, you can see that from the construction of magic T, there is whichever color it, no, the blue color, which is there is one T, and if you take this another one more arm, this is another T which is here. Okay, I hope you can understand. One T, the line is coming from bottom to top. One is coming from the in the horizontal. One is in the vertical. So there's a two T. One is of course H plane T. One is a this is my E plane T. So when I connected, so it become a magic T. Okay. So what is that? The magic T says that whenever power is fed into the one of the port, it will be divided between these two. So no power will come here in this port, basically. Okay. So if I say that, so magic T is general is used for a power divider. You can see that the application here. So the power is spreaded into the one port, it will be divided into two, so nothing is coming here. So I can use it like a power divider, and also I can use it like a coupler. Just opposite of a divider is a coupler. So why the name called magic T is, if I give the any power in the side of this port, you can see my the mouse cursor. So if I give it in this port, nothing will come here in this port. So the power will be divided between this. So it's actually the magically disappear between this, even though it is a straight line. So that is the reason it's called the magic T or hybrid T. So that is the reason. What is the name? Why the name came as a magic? Okay. So these magic T is used in the few places. For example, when he wants to use that antennas connected between these two, so only I have a one source, I have a two antennas. I can actually, use a one source to feed the two antennas so that it will be used in the magic. Okay. So what we analyze using this experiment is typically I'll try to design this magic T and simulate it. So design part, you could ask me, we are not using any design equations for what to design basically. So I have to design by magic T for solution frequency of 4 gigahertz, and so when I fix the frequency, then I have to see that what are these dimension. Basically, I should have. Okay. So how to get this dimension? So in the manual, it is given. Actually, I can show. You can see it here. So now you can see that this is my width. Okay, this is my height. Okay, and the length. The length is here. Is that clear? So one thing is the width, whatever the width we are using it in this width. Okay. So one is a height, this height. Okay, one is a width, one is height, one is a length. So what is the length I should choose? Okay. So this is, you can see that typically it is 50 mm. So how much it is close to 5 centimeter. So this is, you can see that this is my one arm, which is I have this, and this is another arm, and this is another arm. So what I mean to say, the dimension is this dimension. This is the width and height and length. This length has to be fixed. So this is what you say that three-port device. So you can see there is this line. I mean to say this line and this line and this line. So all are actually aligned to the horizontal to the ground. So this is the H-plane T. So and the next one is the same three-port device, and you can see that here uh, when I keep this port, this is, can you see the difference? This is my horizontally is there. I think the quality is on. Okay, this is my horizontal line, and next to port immediately this is horizontal. But when I see this another T junction is just a top. Okay, this is my E plane T. Okay, so when I take this E plane T and H plane T, when I club together, so I'll get the magic T, such like this. Okay, so I'll get this kind of the magic T, something like this is my probably now it is better. Okay. So this is I will get one. So again I'll get the same. Again I'll get the same. Only the top you can see that there is a 4. I think this will be a better top. So you can say that this is a one port. There's another port here, another port here, another port is in the top. So this is the first port. This is a 2 port, and this is mean to say this is 3 and 4. Sometimes this is 3, 4. They will tell. So one thing is to keep it in mind the port numbers. So when you say that particular port, so the port number also will change. Okay. So here, so normally we have a test bench. Maybe you can see it from far. When you come to lab, you can see that. So these devices, you can see that from long distance. This is my RF. You can see that this is a power supply, RF power supply, and I have that typically, I have a AM modulations, what kind of modulation I'm going to use that. So when it comes to the hardware experiment, we will see that. But as doing a simulation also, we supposed to know that how this micro test bench is working on, and how to actually do the experiment with the different devices. Okay. So as of now, you just think that this is RF power supply, which will give very high power to the crystal oscillator, which is actually right on. You can see the company also, made in USA. So basically, it is a 8 to 12 gigahertz crystal oscillator. This is a crystal mount, and this is to generate very high frequency. Then it is connected to the isolator. After that, it is variable alternator. So where we can actually control the power, which is going to the test bench. Okay. So there are when you see the third unit, there is a klystron source. There are two supply. One is a here rippler voltage, current, and rippler voltage. This is the beam voltage. So there is a two voltages record. I can control the beam voltage with these two knobs. So basically, this beam voltage is used to start the electron will start transmit, and the rippler voltage is going to reflect the electron so that it will start coming back into the starting point. So it become an oscillator. So that is a function. You can see it later. So typically, it is a two voltages will be there in the klystron source. Okay. So after that, we have a frequency meter. So frequency meter, you can see that there are different lines and numbers. So it's typically, what you say that these are the frequencies starting from 8. You can see it from the bottom scale. So typically 8. So all the way it is going to 12, 11. This is 11.85 and 12. Okay. So using that, we will measure the frequency. This is a slotted section. This is normally used. You can see it in the textbook Bowser also. So this is normally used to find out the VSWR, and also I can find out the unknown loads. So if I don't know load, I can find out the impedance. So what is the load impedance also I can find out using this slotted section. So after that, I have this crystal detector, which is a cable connected to the oscilloscope. And this is my matched, the other part is matched with the impedance, which is going to be a wave impedance inside the waveguide, so that there is no reflection takes place. So to protect the reflection going back to the klystron source, I have isolate. So it will allow only one direction. Okay. So I have a, here is the, what is that? Oscilloscope. So to see that whether I'm getting a microwave signal. Okay. This is the basic setup. So what the topic of today discussion is the magic key. So you can see that the 4-port device, and there is here. Okay, you can see the difference basically. This is 1, 2, 3, 3-port device. So I have a 1, 2, 3. You can see that all are parallel. Okay, parallel to the ground. So this is the H plane T. So you can see it written here. In case if you get confusion, this is H plane T. All the ports will be a parallel. Okay. And here, when it comes to here, these are also 3-port device, but when you look this is the first port, this is my second port. So another T junction actually in the top. Okay. This is actually, when you see that this is looks like a parallel, but this looks like a parallel, but when it comes to here, you can see that now, if you look in this way, it is all vertical to the ground. Okay. So this is the construction of the E-plane. So it is written, not written here, but you can see that somewhere they missed to write. Maybe they sticked it probably. I don't know. So they sticked above with some barcode. Okay. So this is a E-plane. So what I have to do is take a S-plane T and put it here, just top of it, put E-plane T. So this is just same axis, this is the same axis, and this is the top. When the E and H plane is clubbed together, we will get the magic, something like this. So this is my parallel, this is parallel, and and this is parallel, and this is something vertical. So this is a design for no expand. So since it is a expand, the dimensions are whatever the dimensions of this wave. So this is a width. This is what you say that height. Okay, this is my length. Is all designed for expand. Okay, so this will work only for expand. So that if I want to change the frequency, I have to change the. I have to get a new waveguides. Okay, so that is what I would want to tell you, and probably I can use these options to show the antennas. So you have done a patch antenna and just show that real antenna what we have it in the line. Okay. So meantime, just be on the line. So this is the directional coupler what we have done actually studied in the no, third unit. And the directional couplers, the waveguide form, I'll show that. This is my microstrip form. This is exactly C band, typically 4 to 8 gigahertz. Okay. And this is a power divider. So again, you can see it in the, this is a resistive power divider. So typically this is what you have. If you give 1 milliwatts power, you will get only the, what do you mean to say that you'll get only 0.5, quarter of power in the output. So if you give 1 milliwatts, you'll get only 0.25, 0.25. So only another half of the power will be wasted here basically in the resistive load, which the balloon structure. So this is actually that we won't get actually no power is divided will be same, but the power loss will be there. So it's a resistive power divider. This is also C band. Okay, and when it comes to this antennas, there are two types of antennas typically. This is all antenna arrays. So what you can see that here is the patch antenna I was looking, they might have kept it somewhere. So this is my dipole antenna. What you have designed in the HFSS is using the design software you have done with probably the rectangular probe feed you have done. This is actually the HFED. So you can see that antenna which is printed onto this dielectric substrate. And what you can see that peculiarly the structure which is in the bottom. So this is a top dipole, and this is in the bottom is another. Okay, so you can see that one side is no, this is a small dipole, and this is small dipole. If you take it reverse, this is just opposite printer. Okay, so in effective, you have that one more off will be there in the bottom side. Okay, in this side, in the bottom, you'll have another antennas. Okay, so why this balloon structure is to match the impedance, because when you see that coaxial cable, this is a 50 ohms. So when it comes to radiator to the radiation, the wireless space is typically the wave impedance, array wave impedance is 377 ohms. So to match the impedance, we have this structure in the bottom. So all the antennas will have that. So this antenna looks bigger. So Bigger is means that relatively little less frequency. That's what we say that C band 4 to no, 8 gigahertz C band antennas. Similarly, there are different antennas. So patch antenna also will be look like this. Okay. So I'm showing the antenna. You would have done the first experiment simulation. This is what exactly the antennas, the Yagi-Uda antennas, one more straight. This is what you we'll do it in the olden Doordarshan TVs. You know, that is this is something like this is Yagi-Uda. This is like a log periodic antennas. So you will get a higher gain in these antennas. Okay. So basically, these antennas actually printed onto the substrate. Okay, so this is a broad thing, and let's come to the horn antenna. Let's show that horn antenna. Okay, this you can see that this lab it's like a trip. What you say that no, so seeing that all the components. So you may join in the next week, but better to get some what you say that virtual tour probably. Okay, so here my test bench, as like I told, I have a RF source here, and this is my typically my Klystron oscillator. This is my isolator, and the power will move only one direction. And this is my alternators, my frequency meter. Particularly, this setup doesn't have a slotted section because I don't need a slotted section for antenna experiments. So this is the horn antenna typically. This is your simulated. So what you have done in the simulation, probably you have changed this. If the frequency is not coming at a design frequency, you might have changed this flare length. Okay. So by changing the flare length, you can actually do the impedance match. So what I can do is generally in the experiment, I'll send the have a test bench. I have an antenna connected here. This is a transmitting, and the receiver side, I have another antenna to receive this. As like I have a again crystal detector with a coaxial mount, and this will be connected to the oscilloscope. So I can find out how much power is transmitted and received. So I can measure actually the gain of this antenna. Okay. So however I've done the simulations, I can do the design. Actually, practically, I can measure what is the gain of that. Okay, so these are the normally the setup. Okay, apart from that, there are a few things when it comes to lab. I think we can do that. Okay, so probably with that, no, if you have any doubts, you put it in the chat. Okay, I'll try to go to the experiments and try to. Okay, so I'll just close the screen. So what I'm trying to do is today we'll see that the magic P, whatever I shown in the pictures, now whatever in the real-time waveguide, when you're simulating it, so what are the changes supposed to have to take it in the software? So I request you or suggest you to complete all the simulation experiments because actually it will help you, you know, when you come for a lab, you can actually concentrate more hardware experiments and also you can concentrate on classes. So probably, you know, you can save the time basically. Okay, try to get the software and try to use that. So I'll try in home. It is very straightforward. There won't be any doubt when you know, just you can easily uh, get the answer. So not a problem. So this is my no screen, which is HFSS electronic desktop. So what I'm trying to do is in this experiment is try to find out the S parameters as like I told you. How will it work like as like whatever design? Okay. So S parameter is typically what is the ideal S matrix for S magic T is write it here. Okay, the ideal S matrix for magic T. I'm going to assume some port numbers, but be careful about when you're simulating it. If lab, if it is something, it is a different port number, then this S matrix will change accordingly. Okay. And let me take this is 3, this is 4. You can take this is 3 or 4, whatever may be numbers, the same thing should be reflected into the S matrix. So since it's a 4-port device, I have a 4 cross 4 matrix, and all ports are matched, so diagonals are 0. Okay. And as you saw that in the experiment, the power is divided between these two. When you're giving here, the power will be divided between this 1 and when you give the power at 3, power will be divided between 1 and 2. So when power is divided, what is S matrix? S matrix is just a square root of it. Square root of power is S matrix, 1 by root. So when it is divided, especially in this 3 port to the 1 port, actually this 3 port to the 1 port, the power will be divided half, but between 3 and 2, there is a lot of mosquitoes. Between 3 and 1, the power will be divided, but between 3 and 2, the power will be divided, but just a 180-degree phase shift will be there. Okay. So this is between 1 and 3, it is 1 by root 2. 3 and 2 is minus 1 by root. Okay. So what is this S13 or S31 is 1 by root. S13 and S31. Okay. And S23 and S32 is minus 1 by root. S23. So maybe I have to write it a little bigger. So probably what is S matrix? Just this S matrix is usually asked in the Waveguide. It's actually the basic things that to be known before doing the simulation. So S13 is 1 by root 2. So S31 is 1 by root 2. S23 is minus 1 by root 2. And S32 is minus 1 by root 2. And 3 and 4 is are isolated. So S34. If you give any power at 3, nothing will come at 4. So this is 0. So S34 is 0. S43 also 0. S12 is 0. S21 is 0 because S12, 1 and 2 is isolated. Okay. So let's come to S14. Here also power will be divided between 1 and 4 and 2 and 4, but without changing the phase. That is the explain we gave it. Okay. So S14 is 1 by root 2. S41 also 1 by root 2 because S14 equal to S41. S24 it is 1 by root 2. And S42 is 1 by 2. So this is a magic T. So when it comes to the results, what we got it here. Okay, this is you understood the animations. The power is divided. So when it comes to the S matrix, you can see that some of the there are 3 lines. So it is actually plotted. What are the things is plotted here is S11, S12, S13, and S12. We don't know which numbers is used here, basically in the simulation. So to know that, we have to go to port numbering, and we have to see that. So you can see that the first port, the first port P1, first is created. That's the top. Okay, then the port 2 is created. That is the left side. Okay, and 3 and 4 is created. So let us take probably this is 3, 4. Probably we can guess that this is 1, 2, 3, 4. Let us go with that. Okay, 1, 2, 3, 4. Okay, this is top is 1, this is 2, this is 3, this is 4. So in an exam, you may have some why should have a different either I have the same numbers with one, it will reduce the confusion. So that is correct. So either you can change it here, the port numbers, or you have to change it here. Okay, you have to change the numbering here. Okay, however, I'm just for explanations, I'm trying to say that this is my 1, 2, 3, 4, like that. So with that, you see the S matrix. So this is exactly coming at no, close to minus 3 dB. There is actually the two lines the overlap each other, because if you take S, if you take this, for example, let us take this figure itself. If you take S12 or this is S12, this is S11, S12, S13, S1. Okay, so either two ports will have the same value because the power is divided. So the minus 3 dB is supposed to be S12 and S14. Okay, so the two numbers, since it is the same value, so that is the reason the pink color is overlap with the two S values. That is, I mean to say this S11 and S14. So both, sorry, S11 is a return loss. S12 and S14 both is overlap with the pink color. Okay, what is the S11 is the return loss. Typically, the return loss of the magic T is high, that is close to minus 50 dB. And if you take that S1, 2 and S14 we have done, and S13 is typically should be a what I say that it's supposed to be isolated. What I mean to say that this thing. So when I take this number magic T, S S12, S13 and S14. So 1 and 3 is supposed to be isolated, right? As per this numbering of the experiment. So SN3 is supposed to be isolated, but still I'll get some power, but that is acceptable. Okay, that is a minus 12, close to minus 12. So this is the isolated, this is my return loss, and this is my off the power division. So this will clearly tell me how the magic T is working. If I get this graph for my design frequency, that's good enough. Okay, at design frequency, typically 4 gigahertz. So I have that minus 3 dB two values for two different ports, and typically minus 10 dB for isolated ports. Typically very high value for a return loss S11. Okay, so this is what we need to observe whether the magic T is working like a magic T. So that's what this experiment about basically. Okay, so the steps is there are small difference will be there. I think after that, madam will continue. So I'll just few things. So, so what I do is I'll go to the experiment. So you can see that, okay, this option typically setting the tool options. This is we have done already. Start the programs already. I started. I got the screen. So what I have to do is create new. Okay, create a new and project. It will automatically create this. Okay, HFSS will create the project. They know this now. So the project will be created, and inside you have HFS design will be created. Under that, there are a lot of sub folders will be created. This is a definition is there. So once project is created after, by giving new, go to these are the settings has to be enabled. Now, for example, tools are options, right? So tools, there is no option is available. Option is there, the general option. So what you have to go here is HFSS option. So let me go to the general. Just minimize this. Okay. So here, data entry when creating new boundaries. Use this wizard. So some of the option is automatically default. You don't need to do it actually. Okay. So this probably I'll come to this. Materials also no need to touch. Now this is the things they want to do. Use the wizard for data entry while creating new boundaries. It's automatically it's already is enabled. Okay. Duplicate boundaries with geometry also enabled. And tools option, 3D modeler options, we have to go. So 3D modeler is here. Okay. And in that inside, go to operation, automatically cover closed polylines. That is not enabled. Not here. Probably 3D modeler here. So polyline creations is there, no? That is not enabled by default. So make it automatically cover closed polylines enabled. Okay, that is one thing you have to do. And the drawing, edit property of new primitives is already enabled. So no, we no need to do it. Then here, probably
So just tell them that XYZ, no? That is important. You just tell them the important task. The remaining things they will do it.
so we'll continue for some time with that. So one thing is, one thing I'll just that I will
Where they will
give
do
assistance.
mistakes, only that.
So here, in general, not in the general HFSS, solution type, it should
Sir,
be a driven terminal. So as mentioned here, probably, it's a driven model. Okay, this has to be a driven model. This is we can have to go to the here composite excitation. So only two things has to be done. And after that, Madam will start explaining these steps and how to do it. Okay. So thank you for listening. I give to.
If you can see here this coordinates, no, make sure that the coordinates is set to this values. See, otherwise, no, what would happen? You will not get the codes at exact point, and then everything you have to redo it. So make sure that your x, y, z coordinates are in the position of minus 25, 10, minus 10, and 0. Whenever you are giving the port numbers, make sure that you are giving the port numbers properly. Any doubts? See, there cannot be any doubts. Why? Because you haven't started working on it. That's why I told you guys to somehow get the cracked version. Okay, fine, no issues. Just try doing it. If not, once you come for the offline lab, we will see it.